Hello and welcome to this week's edition of the Applied Deep Learning course. Today we're going to take a look at convolutional neural networks in the context of visual computing. Last week we talked about the three parts that are required for machine learning, which are a model, which is the set of computational rules that we employ on our data to get some output. The second thing was the loss function, which tells us how good we're doing at the moment. And the third part was an optimizer, which says how to improve, how to get to a low loss. And we talked about the specifics of how deep learning has all these three pieces in place. And one of the things that, when you think back about last week's lecture, was what is a gradient? And the gradient is the loss surface that we can compute on our input data. So we have a certain loss function, and when we put data into our model, we compute this loss, and when we compute the gradient, it's sort of a surface in our mountains that we need to navigate. It's kind of the landscape where we want to get to the lowest point. And the way we get there is gradient descent and backpropagation. Gradient descent was this idea of taking a small step in your surrounding area, first basically computing the gradient in your local area, and then taking a small step into the direction of the steepest descent. How is this being done? Because we have millions of parameters that we could tune. That's what backpropagation is good for. So backpropagation was the idea of saying, okay, we forward our data through our network, we compute the loss at the output, at the last layer, and then we backwards adjust our parameters in such a way that we get to this lower point. And backpropagation was the mechanism that gives us the opportunity to compute the partial derivatives with respect to each parameter. And if we know the partial derivative of each parameter, which is the descent, we just have to update all of these parameters with a small weight into that direction that the gradient points us towards. We also talked about the biological neuron, which inspires the thing that is kind of the basic underlying idea that we're talking about here, which is a neural network. And the biological neuron had our dendrites, which were the inputs. It computed something in a biochemical way and then produced a signal on the axon, which was forwarded to other neurons. We tried to replicate this idea with an artificial neuron, which takes some inputs as real valued numbers, computes the sum, multiplies before they sum it, multiplies each of them with a certain weight, computes an activation function, and then outputs this to the next neuron. Again, an activation function is basically telling us whether this thing should fire or not, or how strong it should fire. And it's the nonlinearity in our network that we really need to avoid our entire network of mathematically collapsing into just one matrix multiplication. We also talked about the neural network. So if we have a single neuron and we arrange them in a certain way, we get what we call a neural network, which has input layer, where we just feed in our data, an output layer, and some hidden units in the middle, and it can have a bunch of layers here. One thing that maybe wasn't that clear last week, this network in particular that I'm talking about here is a so-called feed-forward network, because data comes from one side, travels through the network, and leaves on the other side. There is no loop, there is no information going backwards. So that's why this is called a feed-forward neural network. There are neural networks that have loops that are going back, and we're going to talk about them next week. But for now, let's talk about feed-forward neural networks. One thing that you can probably already guess from here is the most pressing question. how do I do this thing? Or how do I know which neuron should connect to which other neuron? Or how to wire them? Apart from, okay, I'm just passing them all forward in the feed-forward network, or I'm having maybe some loops in there or not. Well, the simplest idea is just wire everything with everything. So if we have a neural network, a multi-layer perceptron would be the following. We have one input layer, one output layer, and a number of hidden layers in the middle. And now all of the neurons that are at the same layer are connected to all neurons of the previous layer. So if we have 5 inputs, or let's go back here. So we had 3 inputs, and the next layer then would receive inputs are connected to all of these input layers. Keep in mind that this schematic that you can see here is not a fully connected layer, because there are some red and orange dots that are not connected at the input. So if we do connect every neuron to every neuron of the previous layer, we would call this a so-called dense or fully connected layer, that particular layer. So can we use multi-layer perceptrons for images? So just take a network which takes as an input an image. We flatten that image somehow by just taking one row at a time to get like one large array of inputs. Those are our input neurons, and then have a bunch of hidden layers in the middle, and then produce some output. So if we think about a simple 2-layer multi-layer perceptron, we could kind of think about it in the following way, that the first layer would kind of try to make some sense of these pixels and learns to extract features. And the second layer then would be in charge of classifying them to do whatever we want it to do. For example, image classification. The problem is that this is way too hard and does not work. So if we just have 2 layers and it doesn't work, well, how about just adding more layers? I mean, it seems reasonable to just add more layers here, and ultimately it will kind of learn to extract meaningful features. The problem with adding more layers to a multi-layer perceptron is, though, that the number of parameters quickly explode. So if we have just a small 128 by 128 RGB image, which has 3 layers for red, green, and blue, and just 500 hidden neurons, and they're all connected to each other, we've already 25 million parameters. And this scales exponentially, as you can see here. So if we double the size of these images with 500 hidden neurons, we already have 75 million parameters. And this quickly explodes. We're just having like 500 hidden neurons here. So, and if we add more layers, we would kind of blow up really, really quickly. So, especially with MLPs, we also see one other issue, that the performance typically does not improve at all or much after adding a 3rd layer. So if we add a 4th or a 5th layer, the computational, like the algorithm that basically has so many options to tweak this, that it becomes really hard to get any improvement at all. And most importantly, think back about the first part where we said we use this MLP for images. How do we get an image into this? So I just said that we could squash it. We could flatten the image into a one-dimensional thing. But think about what would happen here. If we flatten an image into a one-dimensional array of numbers, well, we would actually lose a lot of information, the spatial information. And we would lose certain spatial relationships that the network actually could use, because things that appear nearby in an image are often related. So it doesn't really have an understanding of images. So what could we do instead? Well, we need this sort of understanding of images. And in images, we know that pixels that are nearby are often related, and we need to extract a meaningful representation of this. So, how do we get a good representation here? Well, back in the days when we had rule-based systems for all of these tasks, we had a certain input, a developer sat down and he had an idea, so he wrote it into a piece of, in a programming language of his choice, into a piece of software, and then it will produce an output. But it had no explicit representation, it just had the rules that the developer had in mind that he put into a piece of software. With classical machine learning, we expanded this idea and split up this entire problem solving from one step into two steps, where we said, okay, maybe we can kind of extract some features from our input and then map these features, let the machine map these features to what we actually want in the output. That's classical machine learning. And when we now talk about representations, we want these features that are being used to map to the output not to be hand designed by someone who's thinking about, oh, I think maybe edges and colors are important here, but we actually want the machine to automatically extract meaningful features by itself. That would be then representation learning, and this is kind of the main gist of what we're talking in this course, that we're trying to go away from handcrafting, feature extraction, and using deep learning to do this. And the final step to go from representation learning to deep learning now is that we kind of have many layers, and they work in such a way that they learn to extract simple features in the first few layers, and then more complex features in middle layers, and the most complex and meaningful features in the topmost layer. And then these features can be mapped to our output, and all of this, all of the gray boxes here, can be learned by the machine and should be learned by the machine. So again, bringing up this image that we've already seen a couple of times, when we talk about images, some low-level features that the network could try to extract are colors or edges in the first few layers, which it has to extract from the raw input pixels. Then it could extract some more meaningful features like contours and corners. And ultimately in the third or fourth or whatever layer that we have on our hidden layers, it can actually try to extract object parts and entire objects. So using fully connected layers for images, as I said before, might not be the best idea, because it's really like we have lots of connections, and it doesn't really help if you have the information that in the top left corner a pixel is blue and in the top right bottom corner there is a red pixel. I mean, what information would that give us? Right, not much. That's why the idea is to use a different kind of layer, which is called a convolutional layer, which is really the thing for using for images and image processing. So a convolutional layer comes from this idea that spatially close pixels are highly correlated. They belong to the same object, so they should be processed together. So instead of using all pixels, all inputs as input, we kind of take only a small grid of maybe 3 by 3 pixels or 5 by 5 pixels of a certain area, and that is our input for the neuron. And only that, not the entire image. So we can arrange them here. So when you take a look here, we would have the layer L-1, which is an input image with 3 color channels, red, green, and blue. And you can see in the left bottom corner a 5 by 5 grid of each input channel, and these 3 by 5 by 5 pixels would be our input for this one neuron at the next layer. And there can be just one more thing to add here. So this grid here can be like typically a 3 by 3, 5 by 5, or a 7 by 7 grid. So when you think now of these grids, all of a sudden our weights are not just a list, but an actual matrix, because we have not only the pixels, but also coming from multiple channels. And every neuron learns to extract features in this local neighborhood that it sees. So it's only seeing a 3 by 3 grid of the image, or maybe a 5 by 5 grid. But that's exactly what we want to have here. And the good thing is every neuron learns to extract different features. So when you think about extracting features from an image, these features are typically useful anywhere in the image. So if one neuron is successful in figuring out that there is an eye, well, that eye could appear probably anywhere in the image. So we would like to reuse that knowledge. And to enforce this, we're doing so-called parameter sharing between neurons. So all the parameters that we use for all neurons in a single layer are the same. We kind of fix this to only have one set of parameters for all the neurons in a single layer. That means each layer in turn can only learn a single feature. Right. But it can learn to extract that feature anywhere in the image, which is good. But now when you think about just having one feature per layer, well, we need a lot of layers to get anywhere. So what we do instead of just having many more layers, we replicate this. So we replicate the neurons d times, which is a new hyperparameter that we have to tune and change. And what we do is we replicate each layer d times, and each depth slice is called a feature map, which again learns one feature. So only neurons that are in the same feature map share the weights, and by replicating the layer d times, we can extract d different features in this one layer here. And this is how it could look like. So we have our input, which is a 24 by 24 grid, and then we kind of extract features, and we take, in this example here, 4 feature maps. So we'll replicate this, and then we process this and eventually maybe get smaller with the image size, but it have more features that are relevant that we extract here, which, if you think about it, makes sense that we kind of in initial first few layers only have a few feature maps, because those will be very general features like colors, or maybe some kind of gradients. And then as we go further up in our hierarchy, we have more meaningful features that are more specific, so we would like to have more different feature maps here. And ultimately, we produce a certain output. So let's take a look at how this actually looks like in code. I'm now in Google Colab, and what you can see here is a small example that I've prepared for 2 of the most popular deep learning frameworks that I'm using. So there are a bunch of deep learning frameworks that feel free to use any of them. I will be showing you most of the examples in PyTorch and TensorFlow or Keras, which is now pretty much the same thing. So to create a convolutional layer in PyTorch, you basically import the library and then you say create a new conv2d, which is a 2-dimensional layer, and we say our input channels, we have 1 input channel and 16 output channels, and our kernel size, which is this grid that we specify how many pixels it should see from the input, is 3. So we'll have a 3 by 3 kernel, and the stride is 1. So what is the stride here? So, let's run this, and as you can see, it created this convolution layer. So the stride is when we take a 3x3 grid, we're not only taking a 3x3 grid on the left top corner, but we take a step to the right and we take the next 3x3 grid. But we'll see this in a second with a really nice visualization. So a convolutional layer in Keras is very similar in that we also say conv2d, and here we specify the number of feature maps, 16, which in our case here was the output channel, but here we specified explicitly at the beginning. We say, okay, we want to have 16 feature maps, and then we can also specify the kernel size, the strides, and the difference here between Keras and PyTorch is that we also have to specify the input shape. So what kind of input we're going to have here. So in this case, it will be a 32 by 32 image. And last but not least, we can see here something called kernel initializer, which says he uniform. So this is quite an interesting thing to talk about, that when we start training our neural network, we're not starting on a blank slate. We're starting with some numbers. And the big question is, how should we initialize our network? If we just say, have all weights initialized with 0, all multiplicative weights, there won't be any outputs. And the thing is, people have thought about how to initialize them properly. And the main idea is that you do some kind of random initialization, but coming from a certain underlying distribution. And the way how you do this, he and Gloro uniform, this, or also sometimes called Xavier uniform initialization, this is are the most popular things, and they've shown very good properties. But from a practical perspective, just keep in mind that you have to initialize your weight somehow, but all of these frameworks are using a good initializer by default. So that's basically how you do convolutions in a deep learning framework like PyTorch or Keras. And this is how you define one convolutional layer. So we just talked about the stride, and I think there is nothing better than a short animation to understand what this stride actually is. So let's take a look at this really, really great repository, which has an animation of these strides. And what you can see here is that basically when you have no padding and no stride, so there is this combination of padding and strides. So padding means how should I handle the corners around my image. And if you have no padding, it will just, for example here, when you have a 3x3, so the left top animation here, we have 3x3 grid and no padding and no strides. So it will take the first 3x3 grid from the left top, then move to the right, and then start in the next row. So the output naturally will be a 2x2 matrix, a 2x2 kind of output. So we'll kind of shrink it down. We can also say that we have some arbitrary padding or some full padding in the top right corner. So what will happen now with full padding is that we add kind of a border around our input image to ensure that each pixel will be seen kind of fully, and we don't kind of shrink down the image. So let's take a look at the second row. There we see the effect of stride. So stride is basically saying, okay, I'm not taking a look at every kind of, it's basically the step size, if you will, that we use in our convolutions. So if we say a stride of 2 in the second row here on the left, you will see that it kind of jumps 2 pixels to the right and then 2 pixels to the bottom to extract this. And of course we can combine padding and strides here to kind of to get certain effects. There are some more advanced things that you can see here at the bottom. So feel free to come back here and whenever you see someone is talking about some of these other convolutional types, feel free to check it out here. For example, this thing called dilated convolutional here I think is really interesting. So what it does is it doesn't get a dense 3x3 grid, but it actually spreads it out a little bit. So you kind of see more from the input. Talking about seeing more of the input, the really important term here is the so-called receptive field. So although the neurons are only connected in a local neighborhood and only see kind of a 3x3 grid, the higher layers are actually able to see the entire input image. So how does that work? Well, you kind of have 3x3 in the first layer, but when you think about the second layer that receives the inputs from the first 3x3 grid, it will already be able to see kind of a 9x9, or depending on your strides and padding, but basically you already see more neurons here. So this small visualization here, these neurons actually see already more, and the third layer, the G3 here, already is able to potentially look everywhere in the input image. So that's our receptive field, and it makes sense because the early layers typically learn more local features, whereas the later layers therefore can learn more global features of things that can appear anywhere in the input, anywhere in the image. We already briefly talked about strides. Another very important operation that we can have with convolutions and in our neural networks is so-called pooling. So what pooling does is we can reduce the spatial resolutions of our input, but not the depth. So if we have an RGB image, it will be another RGB image in the next step after pooling. But what we do is we reduce it in size. And why would anyone do this? Because we want to reduce the number of parameters. If we kind of have this large image and we add more and more features, the network becomes really big. So it could be meaningful to kind of say, okay, only give me the most important information here, boil it down to a smaller representation, and I continue with this kind of dense and meaningful representation. That is what a pooling layer typically does. So there are two really important versions of pooling. One would be called max pooling, and the second operation would be called average pooling. And what we do is that we basically take a slice and we extract the maximum number of that slice or the average number. So this is basically what a max pooling with a 2x2 filter and stride 2 would compute. If the right part is our input image, it just takes a look at those four numbers, 1, 1, 5, and 6, takes the maximum number, and that will be our output. Similarly, average pooling will just compute the average of its inputs, and that will be our output. So on the left here you see one example. So if that black and white image would be our input, and we have a 2x2 max pooling, it would extract this into a 112 by 112 image, kind of downsample that image. A brief side note here, convolutions with strides can be an alternative to pooling layers. If you think about a convolution that has a stride and jumps always 2 pixels kind of forward and not just taking the next pixel, but going at a bigger step, which is exactly the stride, the stride does. And we've seen this in the animation already. It also reduces our input, and that can be a good alternative to pooling layers if you're not a fan of this kind of taking the maximum here. And there is some criticism about pooling of some really, really important researchers, but it kind of works in practice, and that's the kind of underlying thing with deep learning. So if things work really good in practice, There might be some drawbacks, but unless you're able to prove why they're bad and you're able to propose something better, people will use it. So when we go back to our neural network, we had some input, hidden layers, and then our output. So when we talk about image operations and visual computing, we need certain activation functions for our output units. Why? Because, well, what do we want to output? If we want to have regression, we can use a very simple thing like the identity function, just output whatever we want. If we want to measure the distance between two objects, well, the distance could be the output of our image. And if we have a classification problem, we could use a so-called softmax activation function. Well, what is a softmax activation function? We already talked about the loss last lecture that we use for regression or classification problems, and the loss that I talked about was the cross entropy loss, which basically measures the dissimilarity between two probability distributions P and Q. And to obtain kind of a probability distribution from this categorical input of categories, we use a so-called one-hot encoding. So we have a single label WS, and we obtain a vector by using one-hot encoding. One-hot encoding is quite simple. We just blow up that thing. We just take a matrix of the number of elements that we want to have. So in our case, if we have 4 classes, T would be 4. We create a 4-dimensional vector. We set all values to 0, and the index of the object that we have WS here, so 3, we would set that value to 1. So the predictions, when you construct this network, the outputs of these neurons are typically not valid probability distributions. And I mean, why should they? We only specify that we take our input matrix, we run a bunch of matrix multiplications, and then maybe some max functions or additions, and in the end we get a value. Why should that value be a distribution? So these values are unbounded and they're not summing up to 1, which are requirements for a probability distribution. The sum of all values here would be 1. So what can we do? We can kind of map the inputs of our last layer, of our output layer, to a probability distribution. And this is what the softmax does. So we have T output neurons, and we regard their output W as unnormalized log probabilities. So we just say, I think these are unnormalized log probabilities, and then the softmax function will do the following. We compute here this function here, and what it does is it squeezes any value that we might have into the range of 0 to 1, and it also ensures that by the normalizing term that we see in the bottom here, that the sum of all weights always add up to exactly 1. And there you go, you have a probability distribution. So in our case here, the softmax would produce these -1, 3, and 1 would produce these probabilities here, which kind of, you can see, correlates. So a high value is a high probability for a certain class here. Talking about neural networks, we've seen the convolutional layer, we've talked about the pooling layer, about the activation function that we should put at the end. So let's put all of these things together to create an actual network. And there are tons of different architectures, and each one of them might have certain benefits or drawbacks. So the main layer types that we will be using when we talk about image processing with neural networks are 3 types: convolutional layer, a pooling layer, and the fully connected layer. So in the body, kind of the front end where we try to extract features, we typically only use convolutional and pooling layers to extract these features. And then at the back end, or the head of the network, we most of the time use a fully connected layer for classification or regression. Why a fully connected layer? Because the last layer of our feature extraction will be a set of features. So if we extract 100 features, we would like to use all of these 100 features to produce our final output. That's why it makes sense to use a fully connected layer in a neural network, but only at the end. So a very simple architecture that uses all of these ingredients and all of these parts for doing a kind of a hello world of deep learning would be to do digit classification after the famous MNIST handwritten digits. And a very simple thing could be, so what is the input here? We have, if you've never heard about this, images that are of, I think, 32 by 32 pixels of handwritten digits. And it was one of the really long-standing problems to get this problem solved, because it came from the postal domain, where they wanted to automatically distribute letters, but they needed to extract those digits in a really reliable way. And there have been many attempts to do this with support vector machines and many other approaches. And this became kind of a sort of playground. And it's a really nice data set to try out different algorithms. So we have these images, 32 by 32 pixels, grayscale, and we have an associated label, the number that appears in this. And we could feed that, we could take this 32 by 32 as our input of like 32 by 32 by 1, because we only have one color channel, the black and white, so no RGB. And then we feed that into our first convolutional layer, which has, say, 32 feature maps. We apply a pooling operation to bring it down to a 16 by 16 image. We do another convolution with 64 features, another pooling operation, and then we feed that into the first fully connected layer with 128 output neurons, and ultimately the final fully connected layer, which only has 10 outputs, and then the softmax layer. So the last one, of course, has 10 outputs because we have 10 different digits, 0 to 9. So let's take a look at how that would look in our actual deep learning frameworks, in our actual code. We're back here in our simple Google Colab notebook, and I'm gonna run this, and then we're gonna talk about what the different ingredients are here. So what this thing does is it's the Keras version of exactly the thing that I've just been talking about. So let's start here in the middle. We can see we have a number of layers, which we call here sequential. Then we create our first convolutional layer with 32 feature maps. We also specify a certain padding here, so the output has the same size as the input. We employ our first max pooling, then we do a second convolution with 64 features, another pooling, and then comes an interesting thing. So we're here at that stage here. So let's take a look here. We have, after the second pooling, we have something which is 7 by 7 by 64. So that's our output of that layer. But when we talk about a fully connected layer, we actually need just to have a single one-dimensional input. So what we do here is we squeeze this, we flatten that layer, that 7 by 7 by 64, into just a one-dimensional thing. That's what is called here flatten. And then we do 2 dense layers, and dense is this fully connected layer. And all of the other things that we can see here, let's talk about the other things that we see here. So the first part is, oh, I'm sorry, so it's not 32 by 32, it's 28 by 28. But you can see here that we're loading the data, and it's automatically giving us a split of input images that are stored in X train, and the associated labels here, Y train. And the second set that we're using to evaluate how good we're performing, X test and Y test here. Then we do some pre-processing because we actually want to have them as float values between 0 and 1. So we divide those 0 to 255 grayscale values to a number between 0 and 1. And here comes the famous 2 categorical, which is basically just the one-hot encoding. And then that is our input. So we have y-train and y-test. So these are, of course, our labels, our outputs that we need to encode. And down here we can see the fit function, which, like, that's our model. We compile it, say we want to use the categorical cross entropy loss that we've been talking about before for classification problems. We use a certain optimizer. We could use stochastic gradient descent, or in this case I'm using ADA delta, one of the adaptive algorithms, and we evaluate this by the accuracy to say, okay, how good are we performing? And we're printing out this nice little summary here, which helps us to understand our network a little bit better. And the fit function now runs for a certain number of epochs. So this is one of the questions that came up in the discussion last week. So when we have our input, which in our case is, I think, 40,000 images or 50,000 images, we actually are going, 60,000 images, which we split into, oh no, so is it 70,000? Okay, so we seem to have 60,000 images that we're using for training and 10,000 samples that we're using for testing. So the network is given the chance to take a look at every one of these images once, and after it has taken a look at all of these 60,000 images, we've completed one epoch. And then we repeat this. We show it the same images again, but of course we shuffle them. So we will shuffle these inputs after each epoch to avoid having some sort of dependencies from one input to the next input. So let's see what's going on here. So it's trained here for 12 epochs because we specified please train for 12 epochs. And after each epoch, it evaluated on our test set how good we're doing. So one thing we can see here, the loss went down, which is a good thing, and the validation accuracy went up. That's exactly what we wanted to have. And in the end, we see that on our test set, the performance is we have a loss of 0.916 and a test accuracy of almost 80% of this very simple network here that has 2 convolutional layers. And what it internally does here, the fit, which I haven't said before, is that we actually run this validation here after each epoch. So when we train on all of our tests of our training data, and at the end of the epoch we check, okay, how good are we doing here, and this is the validation. So in this case we're kind of validating on our test set, which I'll talk about later is not ideal, but for this example it's fine. So we can just monitor our performance and eventually stop when we're good enough. So MNIST classification with PyTorch is very similar, but it's a bit more verbose, which I think is a good thing when you're starting because it helps you to understand the individual parts that are happening under the hood. And in my opinion, PyTorch is also nice because you can debug it in an easier way. So we define our network here again with 2 convolutional layers and 2 fully connected layers, and then we wire it in the so-called forward step. So the forward step is kind of the sequence that we had before. So we start with our input X, we apply the first convolution, then as activation function the rectified linear unit, which happens here. Oh, there you go. So I forgot to mention this. So after each convolution operation, we also add an activation function, which is the rectified linear unit. So we do it here, we also do it here. Here we have to explicitly call this function. Then we have our max pooling layer, and the flattened thing that we've seen before here is now this few minus 1. So take whatever you get as input and kind of make it a one-dimensional thing. And then first fully connected, second fully connected, and our output activation, which is the softmax. Training now happens similarly. We say train for a certain number of steps, and we take this. So what we do here is we move our data to the GPU to just be a bit faster. And now we see the individual steps. I think those are really interesting to see once, because our optimizer has to start with 0 gradient to compute the backpropagation properly. So what we do is we kind of null out our memory of previous gradients that were stored. Then we do the forward pass. So here we move our data through the model and we get a certain output. And while we're doing this, the optimizer is keeping track of all the steps that we took. And then we can compute the loss here between the output and the target that we're going forward. And that now that we've recorded all of these gradients, our optimizer, we can say, okay, please backpropagate now and compute and adapt all of those parameters accordingly. And this is what backward does. So it computes, it does now the backwards pass, all of the backpropagation steps. It computes all of the gradients with respect to each individual parameter. And once we've computed all of these gradients, we can say, okay, optimizer, now please take a step into that direction that points towards the steepest descent. And we do that by saying optimizer.step. When we do testing, we do something very similar. We also move our data to the GPU. We run through, but keep in mind there is one important thing here. We're not computing any gradients. We're not keeping track of this when we're doing testing, of course. And the main function is quite similar. So we load our MNIST dataset here. We load our train and test set by saying train true false. We normalize it here, which is maybe unnecessary, but let's see. So this is actually what we're doing. Again, we're saying for a number of steps, for a number of epochs, we're calling this train function. And we say, okay, you're in that epoch and we're training, and what it produces is the following. So we're already here at the end. So we got an accuracy of 99%, which is interesting that this thing performed much better. Maybe some of this normalization really helps to perform better. Okay, so it trained for a couple of epochs, and it learned to classify digits. That was one of the simplest architectures that we can use. And now let's take a look at a bit more complicated architectures. So the VGGNet is kind of a homogeneous architecture that has been developed some time ago, but it was one of the most famous ones because it was the first one that had this big breakthrough for the large-scale visual recognition challenge, where they try to classify images on a really large scale on the ImageNet dataset. And it has about 140 million parameters, but it was really a breakthrough. And how it works is that it has kind of multiple blocks here, and it uses 3x3 convolutions and 2x2 max pooling between these blocks. And the general idea is that, okay, we take our input image, we make it smaller in the step between each blocks, but we add more information by adding more features, more feature maps to the convolutions. So you can see here, the first layer just does this pooling here. The first block has 2 convolution layers and a pooling with 64 feature maps, then 128. Then we have 3 convolutions behind each other, next to each other, that are processed sequentially, and then the pooling, and at the end we have a really large fully connected layer, fully connected layers, 2 layers that have 4096 features as outputs, and then the final layer that has the number of the number of classes of outputs. We can vary these blocks quite significantly, and there have been hundreds, literally, of ideas of how to change this basic idea of using a convolutional and kind of building clever blocks that extract meaningful features in an efficient way, and do this maybe like for multiple scales. You can, for example, have a bunch of convolutions that you run in parallel. So you have one input layer, you run a 1x1 convolution, you run a 1x1, then a 3x3 convolution, then a 1x1 5x5, and you concatenate all of them together. And what this does is that it kind of takes a look at just a 1 pixel, it takes a look at a 3x3 grid, a 5x5, and all of them kind of at the same time. That would be one of these so-called inception modules. There is also a really important module that is called the residual module, which has 2 convolutional layers behind each other, or basically what you have here is a so-called shortcut. So what you're doing here is you're computing the convolution, but you're also passing on, you're kind of creating a shortcut where the information can flow around the convolution, and then you're summing up the original signal and the output of your convolution. So why would this be useful? Well, it helps the network to do 2 things. One, if you have lots of layers, like really hundreds of layers, it can be really hard for the network to kind of extract information at the first layer that it might need at the 5th layer, or at the 10th layer that it might need at the 55th layer. So this shortcut here allows information to flow past some layers for later stages. So we take this shortcut and therefore allow better information flow. And when you think about the residual module, we reformulate this this block here basically into into a thing that gives the network guidance. So it learns basically in the convolutional filter what it should add or remove from the input X. When you have a bunch of convolutional layers, we end up with what we've seen, for example, a 7x7x64 output. So when we take this, we want to classify it. How do we get to kind of the output? And we've already seen one way, because we want to get from this kind of 2-dimensional features, or even 3-dimensional, whatever features, to this 1-dimensional output for classification. Well, we can just flatten the thing straight away. We can just take one after the other in the row, but that might not be ideal because we can drop some spatial relationships. But it's a pretty standard way of doing, and it works fine in most cases, because those features that are extracted are spatially independent most of the time anyway. So because they kind of extract the same feature anywhere in the input. So it's reasonable to say flatten and then do a fully connected layer. But there's also a different idea of not flattening that, but actually doing something called global average pooling. And what does it do is it takes per feature map. It takes the entire input and reduces it to a 1x1 in output. So that's the global average pooling, and it just takes the average of all of those inputs from one feature map and produces a single output. And that way it kind of preserves the spatial relationship, and it can be an alternative to this flattening and then creating the output. So what you do is you kind of reduce this to a 1x1 by D, and then you already have your your outputs, the number of outputs that you want to classify, for example, and you say, okay, now I cast this as a 1 by 1 by D into a 1 by D dimensional array. And what this learns is actually one really interesting thing. You force the network to learn one class per feature map, because that feature map will be the output of the probability. So it will learn to have in the last layer, before we go into this global average pooling, to have one feature map that takes a look anywhere in the input image and produces a high value if that particular class that feature map is responsible for appears there. The inception network is another architecture where we use this inception module that we've seen before, where we use a kind of aggressive input size reduction in the first few layers, then these inception modules, and at the end this global average pooling that we've just talked about. Instead of a flattening and fully connected, we just take the global average pooling and then feed it into the fully connected layer to produce the output. ResNet is another network that performs really well, and it employs these residuals that we've seen before. So as you can see here, it already has way more layers. So I haven't counted it, but we can see here this is like 20, and there are ResNets with hundreds or even over 1,000 layers. And this residual module with these skip connections really helps them to propagate information through all of these layers. What they're doing is quite interesting here. I've told you before that you can use pooling to reduce the image size, but you can also use a convolution with strides. So what they've done here is exactly this idea. They're using strided convolutions instead of pooling. And again, global average pooling at the end. There are also special forms of convolutions, dilated convolutions, deformal convolutions, where the network learns to not have a fixed 3 by 3 or 5 by 5 grid, but actually say maybe, oh, it could be more interesting to take kind of a rotated version of this, and it learns to extract this in a more reasonable way, and they perform quite well. These are quite new, and they have been shown to work well for many problems. This is something that feel free to play around in your project, because the chances of someone having played around with these things for your particular sub-problem might be quite low. So there are kind of some new interesting ideas, and there are many more kinds of convolutions flying around of ideas how to improve this, which I hope that you will play around in your project. So some considerations when you design your network, when you think about the architecture, is how many layers should I actually use? Well, the answer is it depends really on your problem. You, of course, you might want to add more layers to extract more features, but at a certain point it might not bring any benefits. So this is something that is a big problem, that people don't know when they start how many layers they should put in place. And they also don't know which hyperparameters should I use. So again, the number of layers, the number of feature maps, all these are hyperparameters that we have to determine somehow. The grids, and how we can do this in an efficient way would be something like grid search or random search. And there are nowadays even things that kind of try to automate this process and automatically find a good network architecture for you given certain constraints. So, but the simplest way would be to just say, okay, I restrict myself to anywhere between 16 and 40 and 64 features for each of these convolutions, and then you try grid search. You kind of take 16, you take 24, 32, and some other values, you kind of along a grid. And then you also have some other parameters, for example, the learning rate, and you kind of just compute each combination of these and see which one performs best. You can also do a random search here, which is actually more efficient than a grid search, or some evolutionary search where you see, okay, this tuning here, this performed better, so I'm gonna follow up that, but the other one didn't work out so well, so I'm gonna ignore that. What image resolution should you use when you're talking about visual computing? Well, I would recommend to start with something small and see if increasing the size helps. So you should always kind of try to start with a really small version of your input image because it's faster, you will be able to see if it works or not. And computers are remarkable at extracting meaningful features. So there is this Cypher-10 dataset which has images of objects, I think of 32 by 32 pixels, and those are cars, cats, dogs, and so on. And the computer is remarkable at extracting the class from those tiny images. And humans can do that as well. So you should really start with small inputs initially. Which architecture is best? That's really hard to tell. But my recommendation is that you should take a look at what other people did before, what architectures they've used to solve similar problems. You have to read papers, you have to keep up to date here to see which things work best. Some of the things I'll show you in the lecture, some good practices, but it might be that whenever you're watching this lecture, maybe a year from now, this architecture is already overhauled and there's already an even better version of that idea. Again, there's this idea of having a neural architecture search where you have an algorithm that tries to come up with a good architecture, but these things, as you can imagine, are really expensive to compute. But feel free to play around with it. I've added this link here and see if it works for you. So let's take a look at some of the really cool applications, what you can do with deep learning for image, for visual computing. First thing would be object detection. So we want to find objects, and let's start with this small demo here.
In flames of death, eternal rain, we ride towards the fight. When the darkness is falling down, in the times of tough or right, the sound of evil laughter falls around the world tonight. Fighting hard, fighting on board steel through the wastelands evermore. The skeleton souls will feel the hell that's wasted on the shores. On the blackest flames in hell's domain, we watch them as they go. In fire and pain, and once again bring back. So now we fly ever free. We're free before the thunderstorm. On towards the wilderness, our quest carries on. Far beyond the sundown, far beyond the moonlight. Deep inside our hearts and all our souls. So far away, we wait for the day, for the lights are so wasted in blood. We feel the pain of a lifetime lost in 1,000 days. Through the fire and the flames we carry on.
Apologies if you got a bit scared at the beginning of this clip by the music. So some people have an interesting taste of music. And what I think about this small demo here is really interesting is how fast it can detect all of these things. And of course, it made quite a few mistakes here and there where it classified a gun as a cell phone, but maybe that's not too bad. But it's really impressive that this thing is kind of a real-time object detection, and of course it just took every frame, every single frame, classified and kind of tried to find objects in that thing for all of the objects that it know of, that it think this network was trained on. But I think it's pretty impressive to see how good this thing works and how fast it is. And YOLO actually stands for you look only once, which is kind of the idea of you want to be really fast. So they have a really clever internal mechanism of working on object detection and doing this in real time. So typical computer vision tasks, I've already given away this sort of, but let's talk about them again. We can have one output from our input. So we would say, okay, we classify an entire image as one thing, as a cat, and we have one object here. We might also want to add some more information to say, okay, what is the object that is appearing in this image and where is it? That would be localization, like classification and localization. And if we have multiple objects, we can go one step further and say, okay, well, there are multiple things in this image. Please tell me what they are and where they are. This would be called object detection. And ultimately, you can even go down to the pixel level and say, okay, this pixel belongs to which object. And if you do this, you would get instance segmentation. So here you would get this maps, those masks for individual instances, and each cat would get its own region, and you also get the classification label that this is a cat. There is even something which is, in my opinion, really ambitious called panoptic segmentation, which is kind of the latest thing in research, where they're trying to combine semantic segmentation, where they want to say, okay, this pixel belongs to that class, with instance segmentation here, where we say, okay, this pixel belongs to this class of objects and it's that instance. So we're basically classifying every pixel in the image and we're grouping them by object instance. So here we say, okay, there is pavement, there is the road, person, but there are multiple persons, and we get the masks for each person that appears in the image, or traffic light. And I think this is a really ambitious thing here. And of course you have to always be sure that you can actually classify the background as well. So in this case, the building, the sky, and whatever appears in this. So that is the, I would say, hardest challenge, but this is what is currently being researched. So when we go back to the simple case, we talked about image classification. What would be an appropriate architecture for this? Well, extract some features in the backend with convolutional and pooling layers, and then use a fully connected or a global average pooling layer in combination with the softmax to do the actual classification. If we want to add also the position, we could use the same backend, again, convolutional and pooling, but we would actually create two outputs because we want to know about the class and we want to know about the kind of region where that object appears. So we create the classification head, which is a fully connected layer with the softmax, and we create a second head. Like, nothing prevents us from creating just two branches here. And that one would have 4 outputs and the identity function. And those 4 outputs could be, for example, the X, Y position, width and height, or yeah, I think that would be the most reasonable way to encode the position here. And that would be our network for image localization. We can also do object detection by applying the following naive approach, that we use a so-called sliding window. So we take our input image and we perform classification, but we're not performing it once. We're taking a window and we're taking a look at one part of the image only, and then we're classifying that part. And then we're moving that grid to the next position, and eventually we will get a really high value for the classifier because the object appears exactly in our region. However, that is really, really inefficient and you shouldn't do it, but it's a naive way and kind of good way of thinking about object detection, because what it ultimately does is it says, okay, take a look at different parts here and classify that. And that underlying idea is how object detection is done most of the times nowadays. And this brings us to the faster RCNN. So if you've never heard about this, it's fine. But you will, if you're doing object detection, encounter this word a lot. So this idea of saying, okay, I want to do object detection by finding some regions in the input image and then classifying that is exactly what we're doing here. We're having one part, which is the region proposal stage, that is extracting regions that are interesting for us. And then there is the second stage, which takes these region proposals and classifies and refines them. So we get actually these boxes that we're looking for. RNN was the first thing that used this in such a way that it had an external mechanism to create these proposals, this first stage. For example, there was kind of a bottom-up clustering algorithm that kind of tried to find good regions that belong together, and each of these things was then fed into a network that classified this, as we've seen before. And it turned out that, well, it might not be a good idea to use an external mechanism to generate this. Why not learn to extract meaningful region proposals? And that was fast RCNN, which had the idea of, okay, let's learn where to look and then learn how to classify that. So we had two networks that learned the proposals and learned the classification and refinement. And the last improvement or the last evolution of this was to say, okay, well, we have two networks that are extracting features from the image, that are working with the image. Why not join them in a single network and kind of have multiple heads and then feeding back into this? And this is exactly what faster RCNN was doing. So we have one neural network and that has so-called shared backbone for extracting features. And then we have the following architecture where we extract region proposals. That's our first head that takes these feature maps. And then we feed, that produces something, these region proposals in the output. And we use ROI pooling, region of interest pooling, to say, okay, you say, take a look at the left top corner. Then this ROI pooling layer is in charge of taking the features from that region. And then we take those outputs, whatever the pooling layer then produces, which is just that segment of the input image. We classify it and we refine it. We can also do semantic segmentation where we say, okay, assign a class label to each pixel, but not necessarily to each instance. And one way of doing this could be with a fully convolutional network, where we have a bunch of convolutions that always kind of make the image smaller. And in the middle, we have something really interesting. We force the network to make a decision and say, okay, what is this kind of pixel? And then we do a so-called upscaling or upsampling part, where we use a deconvolutional and an unpooling layer to get back to the original input image size, but with the information which class should be there. And this might sound a bit weird. What is an unpooling or a deconvolutional layer? It's not that complicated if you visualize it. So a convolutional layer is a matrix that takes some inputs, multiplies them with a value and produces an output. And the deconvolutional layer would be the exact same thing, but instead of having a large input and a small output, it takes a small input and produces a larger output. With pooling, it's a bit more tricky because pooling, for example, takes the maximum value or the average, but you can think of it as kind of learning these switch variables. That you say, okay, I have these 4 inputs here, the maximum value is always at the right top. So we learn this kind of switch variable, and when we use that switch variable in an unpooling layer, we can take a single input pixel and upscale it and put that value into the position where the maximum value was supposed to be that we learned from this pooling. Instance segmentation, for example, can be done with mask RCNN, which is basically a fast RCNN as we've just seen, but with an additional head for instance segmentation. So we produce the classification, but we also take all of these pixels that the region proposer gave us and do an instance segmentation with those pixels. Therefore, we get the box, we get the classes, and we get the actual thing for each pixel, the actual class for each pixel, and for each instance. And I could go on and on and on forever, because there are so many different networks that are being employed to all of these different problems, like image classification or object detection. If you talk about object detection, one great resource that I can recommend is this open MM detection, this MM detection toolbox, which is kind of a big framework that implemented many of these algorithms, like fast RCNN, mask RCNN, and also some of these one-shot detectors that we've seen with YOLO before, where we're just taking the entire thing, making just one forward pass, instead of having this region proposer, just having one forward pass and directly producing the boxes. They need some sort of other tricks to make this happen, to make this work, but that's what you can also find here in this repository. So play around with it. It also comes with a bunch of pre-trained models. You can play around with different architectures, with different backbones to extract features, and I think you'll be having a lot of fun. And this is what we were also using for many things in our practical day-to-day business. So this is a really great resource to take a look at. So let's wrap it up. We need good representations and abstractions to do anything meaningful with our input images if we want to apply deep learning to visual computing. And we want to learn these representations from the data. We don't want to create sort of feature extractors like SIFT and SURF and HOC features, which are great on their own, but maybe there are better ways, and we don't want to depend on these things. We want to learn them from the data. And CNNs have this one layer, this one specific layer type, which is a convolutional, that learns to connect this local neighborhood by only taking a look at a small area in the input image, because nearby pixels are typically highly correlated. We have talked about pooling layers that can help us to reduce the spatial size to be more efficient, and there are many ideas how to construct better networks. And different applications, as we've seen, depending on your task that you're working on, require different architectures and different wirings of these to solve your problem. And you might be able to come up in the future with a new architecture that no one has thought of before to be really good at your specific problem. And we'll probably come to this with the other topics that we see in the future, where a clever wiring will solve a problem all of a sudden. And last but not least, the field moves really quickly, so it's really hard to assess the quality of new proposals, because there are papers coming out every week where they say, okay, I've done this wiring different, therefore it works better, and they show that for some data set it works much better. But I guess time will tell, and how time will tell is one of the things that I like here is things that appear in here. They've been that popular and obviously working that well that someone took the effort and implemented it in that framework. So whenever you see that one of these ideas that you find in the paper has been taken up by other researchers, used, and then put into frameworks, that is typically a good sign that you can probably use that and that it's a good thing to use. I hope that you've already started with your project. Otherwise, please start really soon and take a look at the first assignment. Come up with some ideas that you will want to work on. That doesn't have to necessarily be with images. There are lots of ideas in the assignment, and really start to think about your project. And I'll see you all very soon.